All right. Before I get started, you guys all able to watch the first lectures? Was that all okay? And anyone have any questions about course material or anything else regarding the course? All right, perfect understanding. So you guys are ready for the pop quiz. They don't do that here. Okay, cool. So we're gonna continue looking at energy sources today. So last time, which I gather was a little while ago, we're mainly focused on fossil fuel sources. So today we'll be talking about non-fossil. So that's mainly gonna be renewables plus nuclear. Okay, let's see. Does this work? Maybe. Okay, here we go. So non-fossil fuels for electricity generation. So again, sort of a quick survey of our power plants in the US. Dots refer to power plants. Color refers to the fuel type of the power plant. And then the size refers to the capacity, right? So how much power can be generated by any individual plant. Trends again, so last time we were focused on our sort of purple dots and our blue dots, which is your natural gas and your coal power. Today, we'll be looking at orange, which is nuclear. And one of the things you'll notice, most of the nuclear plants are located sort of more in the eastern half. There is one power plants, one nuclear power plant in California. Does anyone know what that is? Diablo. Okay. And so I used to say slated for retirement by 2025, but actually it has been extended as of like a couple of months ago. They decided to renew the licensing. I think they're going to do some kind of like hardware retrofits, upgrades to keep it operational for a longer period of time. But yeah, for I think the foreseeable future, that plant will be around and still generating a substantial amount of electricity for the state of California. We've also got our green hydro, which the Pacific Northwest has probably the largest sort of capacity of that resource in the country. And then you've got your pink solar. See a lot of that in sort of the Southwest area, and of course, wind in gray, which is sort of mainly concentrated sort of in Texas and the Midwest. And we'll see sort of why that is in a little bit. Okay, cool. So we've also kind of looked at the deployments of these plants. So this is showing sort of all of those power plants getting installed over sort of different periods of time, right? And so you can see, for example, nuclear, which we're going to look at first. So that is in red over here. And so that technology mainly started coming around in the 1970s. Up until the 1990s, there hasn't been that much sort of new nuclear capacity installed since then. So if you think about the age of most of these things, you're talking about on the order of at least sort of 30 years old, which typically is kind of butting up against the lifetime of a lot of these plants. And then in more recent years, in the 2000s, you can see a lot of natural gas getting installed. Natural gas plants are actually fairly, well, I'll say relatively easier to get up and running and a lot faster than your sort of traditional large like nuclear or coal plants. So that's partly one of the reasons why you can see this happening pretty rapidly, in addition to the fact that, right, they had the shale gas resource expansion. And then notably over the last like decade and a half, you see a lot of green wind and yellow solar. Okay, so moving on. So nuclear, which is what we're focusing on first. How does this work? So this goes through a process known as nuclear fission. So there are two ways to have nuclear reactions. You have fusion and fission. So fusion is where you combine atoms together, and fission is where you split an atom apart, and that results in a lot of energy being released. So the most commonly used fission material is uranium-235. So this is this atom that you can essentially hit with a neutron, which produces barium and krypton and more neutrons. And so that's what they refer to when you think about like a chain reaction, right? Those neutrons can then go on to split sort of more uranium. So that's kind of the fundamental process for the sort of chemistry behind nuclear fission. And this particular reaction releases like incomprehensibly large amount of energy, right? And so 1 kilogram of this undergoing fission releases about 24 gigawatt hours of energy. So that's like millions and millions of times more energy than you would get from a kilogram of coal. So from an energy density perspective, there is nothing that even comes close to this type of operation. So in terms of the resource availability, this chart is like pretty old, but this gives a general sense of like where the uranium resources are. So we have somewhere between 3 to 6 million tons of the material. And so for a 1 gigawatt reactor, you're using somewhere on the order of about 27 tons of raw uranium fuel over the course of a year. So you can kind of work out the math to see, you know, how long sort of that would last in comparison to some of the other resources that we've talked about and looked at some of those resource diagrams, right? At the end of the day, nuclear plants still operate pretty much identically to a coal plant in the sense that you are still spinning a turbine to generate electricity, right? And so in this case, what we have here is instead of combustion of coal, right, to heat up your steam, instead you basically have this chamber where your nuclear reaction is happening, and that heats up water, right? And so this loop goes to boil the water in your boiler, which then sends steam through your turbine, and then the similar sort of process. Except we notice that there's like a separate sort of closed loop here. And so why do you guys think we do that? Yes. Sorry, was that? Yeah, exactly. So they even show, you know, it's like purple water, right? But it's okay. It's not actually purple, but yes, highly radioactive water. So you don't want this stuff sort of contaminating your other sort of loops here. So you're not sending radioactive material through your turbine, for example. The other noticeable difference is that you don't have any combustion processes happening here. And so in the coal plant, if you remember, they have these giant smokestacks, right, to do all the like filtration of your particulates that are byproducts of combustion. So you don't have any of that here. So you only have your steam towers here. And so from an air pollution, air quality perspective, you could stand right next to the nuclear plants and you'd be totally fine. They do have to deal with wastewater. And so you do have nuclear waste that's associated with this process. And of course, that in itself can be a sort of controversial issue in how you deal with the waste, where it gets stored, and so on and so forth. Okay, so decline of nuclear power. There are sort of many reasons why. So if you recall back to the graph that I was just showing earlier, right, all those nuclear plants were getting built from the 70s to the 90s. Why haven't we built any more nuclear plants since? They're very expensive, okay? And so there are corporations that have tried to build new nuclear plants occasionally, and the process is so extensive that it's actually led to a lot of these companies sort of going out of business. Very strong NIMBY opposition. So this is not in my backyard. So how many people here would be comfortable with living next to a nuclear plant? Yeah, okay. So which is great, right? But you guys represent a like highly non-representative sample of the general population. Yeah, so for better or worse, right? There is a lot of people who are who might be scared to live next to a nuclear plant. Have less sort of knowledge about the sort of operational aspects of nuclear plant, right? Just the sort of association with like a nuclear bomb makes people maybe a little bit more hesitant to want to sort of live next to a nuclear plant. Yeah, in the US, difficult to certify. And so there are lots of standards and regulations and procedures related to not only the operation of the nuclear plant, but to the construction and deployment of this technology. And so that's been very sort of difficult to get up and running, even if you do have sort of the capital and resources to build a new plant. And these days, a lot of the reason why we build sort of nuclear power, or one of the big reasons, right, is that it's a clean alternative compared to our fossil fuel technologies. But now you're getting sort of compelling alternatives in renewable resources, which isn't to say like they provide the sort of same service to the grid, but still, like in the conversation about future power sources, the fact that those alternatives are becoming sort of more and more competitive makes it just a harder case for nuclear to compete. And then the disaster factor, so Fukushima, which was a while ago, but that has led to things like Japan sort of moving away from nuclear power, right? We see similar types of things happening in other countries as well. Okay, I'll pause really quick. Questions? Yeah. Yes. Yeah. This happened like within the last month. They decided it's been long enough. So, but actually, so from so two perspectives, like so safety factor, right? So your ordinary like everyday safety, thinking about things associated with nuclear power, such as like radiation, right? So does anyone know the best place to shield yourself from like radiation in general? Anyone have any ideas? If you were like a concrete bunker, were you gonna, I see you're like, huh? Bathtub. Yeah, so possibly. So actually, so the answer might surprise you. So it's actually inside of a nuclear power plant, right? So people have, because there's such stringent safety protocols, you can actually, they have these essentially little readers for background levels of radiation. And by far the lowest places that you can get in the world are like caves and nuclear power plants. So from that perspective, like everyday safety wise, nuclear power plants actually are substantially safer than almost any other sort of power generation asset, like orders of magnitude from morbidity and mortality better than natural gas and coal power plants. Yeah.
Is it true that the really high capital cost comes from national safety point of view? Like they have to be built in a way that a bomb should not create an explosion?
That's part of it, but my understanding is that a lot of the high capital costs are actually related to some of the like administrative aspects of trying to install a nuclear plant because you have to get so many like certifications and it stretches out the like amount of time that takes to build the plant. Like you have to build something, you have to certify, you do more work, you have to certify. So whereas in some places where you'd be able to build everything sort of all at once, you know, you have to go through these like stepwise procedures that sort of like drag out the time that it takes. I think that's one of the biggest sort of factors that relates to that. Yeah.
They're all pretty much like uniquely designed for that location. So
yeah.
10 acre land that's flat.
That's right. Yeah, exactly. So one of the contributing factors to maybe trying to get the economies better is standardization. And so some companies like Westinghouse have like these sort of standardized nuclear reactor things, but yeah, you still run into some customization issues. Yeah.
One tried to get it for
yeah. So are there any SMRs operational in the US today? No, right? Yeah. Yeah. So for those who don't know, SMR is a small modular reactor. So these are like little portable nuclear reactors, essentially, that you could like put on the back of, you know, like an 18-wheeler truck to sort of move it around. But the whole idea is to be like smaller and more nimble and easier to set up and sort of have lower costs associated with it. It's still like a fairly developing technology. I don't know too much about SMR, so. Okay, so that's kind of our quick overview of nuclear power. Yes?
Do we understand correctly, by 2050, there will only be 2 plants that have a valid license?
These are the expiration dates. So if it's the case that all of these would cover the fleet of nuclear reactors, then yeah, that's right. But what happens is that even if you're not constructing new power plants, sometimes they'll have sort of like license renewals and they'll like upgrade and update the nuclear plants. And so that's what's happening with all of these plants in the green. All of those nuclear plants have their license renewed and then they'll expire sometime in the future. Yeah. Yes.
How has France been able to run the reactors way past their lifetimes? Are they doing something different?
No, I mean, we're doing that too, right? Like our nuclear plants are like 50 years old and they were meant to have a 30-year life, well, 30, 40, some 50-year lifespans. But what ends up happening is you have retrofits and upgrades to sort of modernize the technology. So they'll take down the plant for a little bit, do upgrades, and that is like an alternative to like building a new plant. Yeah.
Also, like
yeah.
I mean, vertically, you're not allowed to have
yes. That's the NIMBY opposition.
But like there's this whole like, the environmental movement of the 70s and 80s, very much against it.
Yeah.
For other reasons that
yeah.
People don't know. It's like shutting down.
So that's that. Well, again, has to do a lot with the sort of popular opinion. I don't think France has had a nuclear meltdown in their country, right? Is that right? Yeah. But we have, so maybe that's why. I don't know. Okay. So that covers our like only non-fossil, or sorry, non-fossil, non-renewable energy source. Yes.
Fusion, like there's.
Okay,
big,
fusion.
big ones.
No, fusion. It's coming in the next 5 years, and 5 years later, I'm going to tell you the same thing. Yeah. Nuclear fusion is always 5 years or 10 years away. No, I mean, there's always. I say that they always have like. I don't know anything about fusion or nuclear really. I'm a transportation guy, but I always read about these breakthroughs in fusion. I'm like, oh, it's coming, and then a couple of years later, there's like, oh, there's a new breakthrough in fusion. No, so fusion is difficult for a number of reasons. So we can now say that you can get energy positive because that was like the most recent breakthrough, right? Yeah.
That's
You don't-
technically no, because the amount of power required to turn on the lasers. So it's like 2.5.
I thought it was even with that.
2.5 gigajoules or whatever in 3.6 out. That was like 4 gigajoules like turn on.
It beats steady state essentially.
Okay, I see. Okay, well, so it beats steady state now. So the
22
next
years? Oh,
in the next breakthrough, it'll beat the yeah. So fusion is interesting from that perspective. It'll be kind of similar, similar in concept to fission for like the rest of how it's generating electricity. But even if it is energy positive and you get to that point where you could like modernize it and you could get it to consistently produce electricity, you still have this conversation about like the economics of it, right? So even if the technology itself works, if it costs too much, if it costs like 100 times more than like a fission reactor, it's still not going to be successful. So there are like technological hurdles that remain for fusion, and then there are like economic challenges that remain for that technology. So just wait another 5 years and we'll see.
The fusion reactor every home.
With sorry, what are we currently doing with the radioactive waste? Like going to space, the bottom of the ocean?
No. It's stored. The vast majority of nuclear waste is like stored like on site with the plant itself. They have tried to do like these sort of more centralized repository locations of nuclear waste, but how would you feel about burying some? Yeah, right. Yeah.
they're a jackrabbit.
Yeah, these things, right? So the key thing, I guess my sort of big key thing about nuclear is like there are a lot of these like technical and technology aspects of that power generation process, but then probably more so than any other power generation, there are a lot of these other like social aspects of it that constrain our ability to use that technology and operationalize it. Okay, renewables. So this is all stuff that's coming from the sun, directly or indirectly, or from energy like in the earth. Okay, and so we have solar, wind, biomass, which would be kind of indirect from the sun, right? Because this is all energy produced through photosynthesis. You've got hydropower, also indirectly from the sun. All of this is driven by the hydrocycle, which is right, evaporation of water from the sun. You have ocean, so tides, waves, and ocean gradients, thermal gradients, and then geothermal, which is heat derived out of geological formations. We are mainly going to focus on solar, wind, and hydro. But if folks have questions about the other ones, I can, or are interested, I can go a little bit more into that. Okay, so renewables. I'm preaching to the choir, I feel like. So, you know, we think that renewables is a key component for sustainability. So you like, even if you are like a climate change denier, like renewables isn't just about climate change. There's the sustainability aspect that eventually, right, you would run out of fossil fuels, you know, whether it be oil or coal or natural gas. And so having quote unquote infinite energy rather than sort of using up limited resources should be kind of a compelling part of that sort of discussion, right? Energy security is actually a pretty big one. So you think about the resources associated with like international conflicts over resources such as oil, right? Energy security has become like an important mandate for even like the US military, in addition to things like GHG reduction for like climate change. And growing very rapidly. I need to update this, but the vast majority of new capacity getting installed worldwide is coming from renewables. Yeah, so non-depletable, widely available, well, non-depletable until the sun explodes in like 4 billion years. They are really actually becoming quite economically competitive. So we're going to look at some numbers, particularly for like wind and even solar these days. You're thinking about from like a business perspective, if I want to make money, it's like, okay, well, before, you know, why would I build wind or solar if I could build natural gas to sort of essentially make larger sort of profits, have more revenue streams, right? And so one way that we make them economically competitive is through subsidies and policies that support this. But now we're getting to the point where naturally, right, businesses are actually going to want to look to these technologies because they can sort of economically compete with some of the technologies that we talked about in the last lecture. Greenhouse gas emission cuts, right? And so that's for climate change. And I should also mention there's associated benefits with air pollution too, which is a big one. Yeah. So what barriers? So same thing as mentioning, generally higher cost, although that is sort of rapidly becoming smaller and smaller. Impacts can vary. So when we think about sort of carbon neutrality, it's going to sort of depend on the renewable source that you're talking about. So not always carbon neutral. And then the other big one is that even if they are promising for climate change, you still can have associated like land use, water use, and materials, especially in the sort of construction of these technologies, which will be important to keep in mind. Solar and wind are intermittent resources. So the sun doesn't always shine, the wind doesn't always blow. So compared to something like a coal, gas, or nuclear plants, right, we can't sort of turn them on all the time, which can be challenging for our energy system, right? Because generally the way our electricity system works right now, whatever we need has to be produced at basically exactly the same time, right? And so that can be problematic for some of these renewables. Yeah, potential interaction with other markets. This is something we'll talk about in like a faraway lecture, but bioenergy, for example, that might be interacting with the production of food crops, right? And so there are these sort of interactions that can happen that can be a challenge or barrier to this technology. And then variety of market entry, social, institutional, and policy issues. Okay, so what are we looking at, sort of looking like recently? So this is renewable power capacity growth. So this is new capacity that's getting installed. So I believe this is this worldwide? I can't remember. Is this US? 3,000. No, 3,000 gigawatts has to be, that's too much. Yeah, yeah. Yeah, so if you guys remember from the like back of envelope calculations, right? Like California capacity, peak capacity, right, is about 50 gigawatts. So yeah, this should be worldwide. But it gives you some perspective of the capacity that's getting installed. So this is what was added, and then this is total. This is cumulative, right? Yeah, going crazy here. All right. So what do investments look like? So countries are putting a substantial amount of resources. China in particular has put a sort of vast amount of investment into renewables over the last decade. So they're kind of, I think they're more than basically everyone else combined or close to that. But still a substantial amount overall. This is in comparison to still investments being made in fossil fuels, about double. But hopefully this continues to grow and this will sort of continue to shrink. Yeah.
What's the difference between the big figures on the bottom right? Investment in renewable power? Is one like half the energy generating?
No, this is just this is a snapshot of 2018, and this is cumulative through the whole decade, I believe. Yeah. So this is what was invested in a single year. Okay, and some kind of trends about what was getting installed. And so even like a decade ago, you can see here, fossil fuel capacity getting installed. This is gas, and this, I believe, is coal and oil. And compare that against what you have here, solar and wind. Versus new capacity getting installed in 2021. So there are these continued shifts towards installation of renewables, and that's starting to sort of dominate the new capacity deployment worldwide. Yeah.
Is this capacity deployment by nameplate capacity? How many gigawatts?
Yeah, nameplate. So yeah, just to be, well, we'll talk about capacity factors in a little bit, but yeah, nameplate capacity, which refers to the sort of peak production of power from an individual plant. It's like maximum capability. And the main difference, right, with a nuclear plant versus like solar or wind is that you could have a nuclear plant basically on for an entire year, whereas which would reflect a capacity factor of like 100%. So nuclear plants are usually like 95 to 100% capacity factor, which means that's how often they're on. Versus, does anyone know what the sort of average capacity factors of solar and wind are in the US? I hear a bunch of people yelling numbers at me. Yeah, so for solar, it's like 15 to 20%. And then for wind, it's like 30 to 40% average-ish. I think wind is now like high 30s on average, maybe hitting low 40s. Okay. So VRE stands for variable renewable energy. So share in annual generation. So this is talking about of the actual energy produced from power plants, how much of that is coming from sort of renewables, right? And so Denmark is mainly wind, and you can see how that has actually grown over time. And so for example, Denmark here, that green bit is the amount of solar that they produced in 2016. And then they added sort of that much blue over there by 2022. Whereas this blue bar here is how much wind that they were using in 2016. And then they've since added that much more generation from wind by 2022. So they're up to about 70%, pretty unusual for sort of most countries. Frame of reference, US is here. So still small, but we've moved from down here like 6 to 7% in 2016 to above 10% by 2021. And then you guys have seen this chart before, but just to hone in specifically on renewable energy here, you can see sort of the percentages, sort of 12%, right? So by 2021. All right. So probably the biggest renewable power generation is actually coming from hydropower resources. So this is a similar chart to the one from before, looking at when power generation assets were being installed. So this is in the US, when hydro capacity has sort of been added into the system. And you can see this sort of peak here in the 50s, 60s, 70s. And why is it that we haven't added much hydro resources since then? Yeah. Yeah, well, not even necessarily land, but you've basically dammed everything. So you run out of the sort of water resources to do this. So basically any major sort of waterway you can think of in the US has been essentially used for hydroelectricity generation. There are very few, if any, like rivers that haven't been dammed in some way to take advantage of these potentials. So from this total, hydro is, that seems low actually. Maybe that doesn't include pumped. 6% of the total generation. In terms of hydropower potential, this is essentially what it looks like worldwide. So the blue, right, in your like Sahara Desert, right, that's where you're gonna have the least hydropower potential. And this is in terms of measured runoff of water, going all the way up to red. The red areas have sort of the largest annual runoff. And so you get the most sort of resources there. And so in fact, we do find that like a lot of countries in Central America and also China do get a very substantial amount of power generation from hydro resources. I mentioned that in the Pacific Northwest, you have actually pretty good hydro resources. So you can see what that looks like over here. And then there's a decent amount in Canada. sort of just north of our sort of US borders in the Northeast that also produce a lot of hydropower resources that gets imported into the US.
More than 9 meters of rain a year.
Yes, it's a lot. Yeah, so you can think about how that compares to, like, we've had rain for what, the last 3 weeks? Does anyone know how much rain we've had? Something like, oh, it was more than a foot. Yeah, okay, but like on the order of a foot. I thought it was like 20 inches, but yeah. So, but think of what that would mean. That would be like those 3 weeks would be still well under like half a meter of rain, right? So that's probably all the rain we're gonna get for the rest of the year. For those of you who are like newer to Davis. Hey, I've been here for like 7 years, and I think there have been like several years where it basically didn't rain at all. Okay. Potential. So theoretical resource is like all of the energy that we could get from all of that runoff, water runoff on land. So that potential is anywhere between like 16,000 to 40,000 terawatt hours. So that encompasses everything, right? So like all the elevation differences, how much precipitation you get, and then topography. But a lot of that isn't something that we could actually capture. A lot of that runoff is going to be inaccessible, and maybe like the runoff can be like dispersed, right? So you're not getting everything in like one big river, so you wouldn't be able to really capture that. And so siting issues. One thing to keep in mind is that, okay, so hydro, oh yeah, sorry, go ahead.
You've got an energy amount here.
Yeah, annual. Sorry, this is an annual theoretical potential estimate. Yeah, yeah. So hydropower doesn't quite operate with the same, we don't really call it an intermittent resource in the same way that like solar or wind would be, right? Where like a cloud passes by and suddenly your solar operation drops drastically. But you can actually almost think of this as seasonally intermittent in the sense that you can have different amounts of precipitation right over the year. So this is the precipitation in San Francisco, sort of averaged over some time period. So when it rains a lot, you get more potential, and then when it doesn't rain very much, you'll have sort of less of that. And so hydropower, depending on the way they sort of choose to operate it, generally you're going to have your highest power production in the like winter and spring months, and lowest power production in the summer months, at least in California. Okay. And it also varies by year, right? And so again, affected by precipitation, and you can see sort of the huge amount of annual the dispersion in amount of precipitation year to year. And so you can have these sort of large differences, which also can have a really big influence on the power production capability of your hydropower. Okay. This should be California. Yeah, this graph is California. Yeah. Okay. How do these things work? basically, remember, right? As long as we can get something to spin, we can produce electricity. So same name of the game. You have a turbine here. So you have water up in your head pond that goes through your sort of facility. And the big thing to remember is that you have a large potential energy difference with the water up here and the water down here. And so that is essentially what you're trying to capture. So this water is essentially has all of this pressure to move downstream. And what we're doing is capturing that pressure by moving that water through this turbine to spin this to power your generator. Okay, and so then it captures that difference in energy state and moves this water down here. And then you produce electricity in your plant. So to calculate this, it's actually sort of fairly straightforward. So who remembers the equation for potential energy? Yeah, mgh, so mass times your gravitational constant times height. So that's actually exactly what this is here. So power, so energy divided by time. So it's going to be mgh over t in some way, right? So you've got your turbine efficiency, which is like how much of the energy that you can actually capture, the density of water, your acceleration of gravity, so that's your gravitational constant. H is known as, in this nomenclature, it's the head, so that's a difference in height, so that's just the H in your potential energy equation. And then you have your flow rate, which is where your per time happens, so that's why you have power instead of energy here. And if you multiply density times flow rate, that gives you your mass, right? And so that's the M part of your potential energy. And so, yeah, you could quickly sort of derive this from just knowing your potential energy equation, but that's how you would calculate the power production of a hydro facility. Yes. Yeah, per time, right? Yeah. Okay. Just for sort of general knowledge, you don't actually need to know the sort of details here, but there are different types of turbines being used in different hydro facilities. So these are a couple of the common ones: Pelton, Francis, Kaplan turbines. And the reason why you have these sort of specific designs is that you can imagine that like the operation of your dam kind of depends on the characteristics of the river that you're damming, right? And so if you have like a really tall one, and whether the water is flowing slowly or very quickly, you can design these turbines to operate within sort of a range of operational constraints, right? And so like Kaplan turbines, typically low flow rate and lower, smaller head size dams. Whereas, if you had like a Pelton turbine, really tall but low flow rate, versus Francis turbines, which is faster flowing water. Yeah, and so these all have sort of different efficiencies that depend on characteristics about the river which you're damming. And so that's why you have sort of different applications of these turbines. All right, any questions about dams?
With a lot of the environmental movements in the Pacific Northwest to remove dams,
Yeah.
is that something that would likely to derail the feasibility of continuing to implement dams across other areas?
Well, okay, I don't know too much about the protests against dams. I guess there's like NIMBYs for everything. But I would say probably that's going to be sort of less of an issue because everything is basically dammed already. So there's not that much like
I guess. maybe
expansion.
removal, like the presence in removal of
Oh,
dams.
okay.
And so,
I think, well, I don't know. I think that would be a pretty bad thing because hydro resources are like really good for a lot of the things that we care about. They're like cheap, they're clean, they're sustainable. I mean, they have environmental impacts for sure. They have environmental impacts, and that's like shouldn't be uh, shouldn't be brushed under the rug for sure, right? But like in comparison to the types of harms that most other power production facilities have, like these are like not that big. Like the like benefit cost calculus of these, like if we could do just hydropower, like if the resources existed to do that, I would probably just say do that everywhere and like forget about everything else. Yeah.
I think the area that's really happening, especially in the Pacific Northwest, has been like small hydro.
Okay.
Like the larger ones are actually generating like significant amount of power.
Mhm.
And you kind of justify taking out some smaller, more damaging ones, but we want the larger ones.
Yeah. Yeah. So like your cost benefit calculation for like the environmental harms related to like a small hydro facility might be different. And again, this is like not my my area of expertise. So yeah, I appreciate you highlighting that.
Central America, Brazil, the biodiversity there,
Uh-huh.
it's exponential to what you might have in Canada or US. So that's where the trade-off is.
Yeah, but their like power production is much higher there too. But yeah, that is true. And but yeah, and maybe I should like add a slide in general about some of the sort of environmental factors related to this. Certainly should be considered, right? We want to think about this holistically in terms of its benefits versus the harms that it causes. So yeah, I don't know too much about the specific environmental factors related to this in certain areas, but yeah.
Yeah, actually, one of the main problems with these kind of activities is that you have to change the course of the actual river.
Yes.
So-
Oh yeah,
and
for
you
sure.
need to- And you need to clean up the area to make the river.
Yeah.
You are gonna change completely the environment.
Yeah, yeah. So from a like a local environmental perspective, these things definitely have a decent amount of impact because you're essentially shifting the waterways.
Would it be to make it, I don't know, a lock-in if we install a lot of hydro capacity and climate change changes the water patterns and water cycle itself. So as you show the graph with droughts increasing,
Hmm.
and production from these declining. So it would not be a bad idea because you're locking in on this hydro capacity that may not be even as useful and may not even get close to that theoretical limit that you showed.
Yeah, that certainly plays a calculus. I mean, people do think about these things, and and to be fair, there are types of facilities that try to minimize like environmental impact, for example, where like you have, if a river is dammed, they build these sort of like lock systems to still allow like salmon to swim upstream and not have to like get blocked by a huge dam, right? So yeah, there are lots of like deeper considerations that go into the design and deployment of these facilities that are important to consider. Okay, we're like flying through all the renewables. All right, so oh yes.
Yeah, we talked about the hydropower about hydropower plants, because I guess they exist, but and like when you saw this world map with potential for hydropower plants, I thought that basically on all the coasts where there are no big cities, you could potentially just put a hydropower plant in there and generate some more energy.
Yeah, I have like a real world analogy for these things. So okay, who knows what the average cost for a megawatt hour is in the average cost of producing a megawatt hour in the US? Does anyone have any idea?
It's like an average 13 cents.
Yeah, you multiply by 1,000. Yeah. So 1,000 1,000 times your, let's say 10 cents. So you're talking about on the order, it's like $10 a megawatt hour. That's like, that could be, that's might be like a closer to a retail price, so it might be a little bit lower than that. So, okay, anyways, where I'm going with this, I think it was the UK, right, that offered an incentive for tidal power. They said, we will pay you $300 per megawatt hour if you produce electricity from tidal power. And guess how many tidal power plants there are in the UK? 0. So to answer your question, like there are, yeah, the technological aspects of it, which is like it takes advantage of the like motion of the waves, right? Transforming kinetic energy into electricity. But the like economics of that power production are like so terrible that I have no slides about them. So yeah. Yeah, so even getting 30 times more money to produce electricity, they couldn't get it to be economical. So okay, wind power. Totally opposite. So these guys are actually very economical these days. So this gives you, again, this chart is outdated. I couldn't find a newer one that goes all the way back to show this kind of steep decline, but right, this is a decade ago, so you can imagine it has still sort of continued to fall a little bit. But you're talking about an order of magnitude decline in price, where now you are actually competitive with natural gas plants, which is like as cheap as you can get besides hydropower. And that has resulted in this, right? So huge growth in wind capacity, particularly so sort of right in the inverse at the same time that these were getting a lot cheaper. There's also policies that help promote this power generation technology, either sort of mandates or requirements to deploy renewables or through economic subsidy policies. Okay, so if you recall in that earlier map of all the generators that we had a whole swath of wind turbines sort of in the Midwest and in Texas. And the reason for that is where the sort of wind potential is. So this map shows you sort of the average wind speed. I believe this is at a height of 100 meters, right? Where is that? Yeah, 100 meters. So your wind speed tends to pick up a little bit the higher you go. And so 100 meters high, you're getting sort of these average wind speeds where the highest are in sort of blue and purple and red, and your lowest is sort of your green and yellow areas. So you'll notice largest resources immediately available on land is sort of your mid, sort of central US area and sort of Western Texas. And then if you look immediately offshore, you have actually suddenly huge potentials. And so red here, particularly in the sort of the Northeast, and then off the coast of sort of California, Oregon area, you get a huge amount of potentials from wind. And so that's what's led to the deployment of a large number of wind turbines here, and then the sort of desire, and actually there has been a fair bit of deployment over the last couple of years to do what's known as offshore wind turbines, which is where you're building them sort of just off the coast. Okay, so sort of some back of the envelope numbers. These are kind of good rough numbers to sort of keep in your mind, right? So a pretty good wind resource. So if you have wind going at 7.5 meters per second, you're talking about energy of about 500 watts per meter squared. Okay, and so if our turbine is, let's say, 25% efficient, then you're getting about 125 watts per meter squared, which annually would produce you about 1 megawatt hour of electricity. So per cubic, or sorry, not cubic, per square meter. So how much area would you need to power your conventional home? That would be the equivalent to about 24 square meters. To power your car, 6 square meters. Yeah, and so this gives you kind of a rough sense of like sort of the size of the wind turbine that would be needed to provide that amount of power. Okay, still a turbine, still spinning something to produce electricity, right? In this case, we don't need to like boil water or anything. It's just the wind itself that's spinning the turbine. So this is a sort of simple diagram of what a ordinary wind turbine looks like. You've got your tower so that it can go up to the heights that you would like to get that wind resource, your rotor blades, and then inside this, what's known as the nacelle, you've got your generator, which is producing electricity from the spinning of the actual blades of the wind turbine. Has anyone ever been in one of these things? Yeah, all right, so what's on the inside?
There's a gearbox, there's a high speed. I used to work at a wind farm, so
Oh, okay. So did you climb up all the time? Oh, okay.
yeah, it's really amazing getting to stand at the top. Something like just blowing at your face.
Yeah. And you, I feel like you get really strong from climbing these ladders all day.
Yes, I was very sore the first time I did it.
Yeah. I saw these guys, I've been inside one. I saw some guy like flying up, like, oh man, climbing those like all day. So they have, at least in the one that I was in, they have these like platforms that go up. So your ladder goes up, there's a platform, and then so that if you fall, like you won't completely die. Yeah, and you're supposed to harness in every time, although my understanding is that that is too much trouble for some people. But yeah, so these things are tall, right? We're talking about sort of these days, your sort of 1 to 3 megawatt turbines. They're getting pretty big. So those blades can be the length of a football field, right?
By the surface area, do you mean the surface of a single blade?
No. It's not surface area, length.
Oh, okay.
Length. Yeah. It's not like an entire football field rotating around.
What's the length of the football?
It's 100 meters. Yeah. A yard is close to a meter. Yeah. So 100 meters. It's pretty big. Yeah. My favorite part of the visit was that they were leasing land from a sheep farm, and so on a hot summer day, what you would see is that all of the sheep would be gathered in the shadow of the thing, and then over the day, like the shadow would move around, and they would just graze along with the shadow, which is pretty funny. Okay, wind energy. This is actually kind of similar to our analogy for hydropower, right? So instead of potential energy, we're capturing kinetic energy. So kinetic energy is 1/2 mv squared, right? Mass times velocity squared. And we're literally just sort of converting that. Energy is equal to the density of the air, the surface area that it passes through, the speed of the wind, and then the amount of time that it takes, or the sort of discrete amount of time that you're talking about as the wind passes through this surface area. So this equation converts directly from kinetic energy. You can calculate the mass of the air via, right, the surface area it passes through times the wind speed times the amount of time times it's the density that gives you the mass of the air, and you come out with something like this. So that gives you the amount of energy that you can grab essentially from the air.
just,
Yeah. Yeah, so for power, you would just get rid of that T, and then that would be the amount of power that you'd be generating constantly. Yeah.
Don't have to multiply by some efficiency or.
Yeah, so this is the energy of the wind itself. And then if you had the efficiency of the turbine, you could multiply by that to get, right, the energy that would actually you'd be capturing out of the wind. Yeah, like one way that I like to think about this is you're not going to capture all of that energy. So you guys know that little like spinny fan thing that you like blow that you get at like amusement parks, right? If you blow into that fan and it's like spinning around and you put your hand behind it, you will feel you would still feel some wind from your right breath, right? And that all of the thing that you feel from your hand is energy that's not captured by into the spinning of the turbine. So that's the same thing here, right? If you were to picture wind blowing into a wind turbine and you were to fly up behind the wind turbine, you would still feel wind, right, coming through. And that's because the wind turbine isn't able to capture all of this energy. So you'd have to multiply it by some efficiency factor here. Okay, growth in turbines will blow you away. These are sort of sizes of turbines. So yeah, I was saying like a 3 megawatt turbine is a 100 meters, so football length blade, but now you're talking about even bigger. So like 3 to 5 megawatt turbines are usually going to be sort of your larger offshore wind turbines. And those are the ones that really get ginormous. And this is like a sort of pictorial comparison of some famous buildings, right? So these things are like as tall as the Eiffel Tower. Okay, as turbines get bigger, so why do we build them bigger? Well, because you generate more electricity, right? So the capacity gets larger. So your nameplate capacity has been sort of increasing on average over time, as well as the hub height and the rotor diameter, which is the thing that's essentially allowing you to get larger capacity, right? Because the larger your rotors are, the more wind energy that you're capturing in the sort of diameter of that wind turbine. The capacity factor of wind turbines has also been steadily increasing over time. And so I was saying we're on the like 30 to 40% capacity factor, right? It depends on the quality of your wind resources, but generally that number has been sort of continuing to grow, especially as like they're adding more like offshore wind turbines, which tend to have higher capacity factors on average. Yeah, and so what do those additions look like? You can see the growth in capacity has been sort of very steady and increasing over the last decade or so. Cumulative offshore wind capacity. So this is all of the stuff that's getting built, out in the ocean. That has been rapidly growing as well. And yeah, probably it would be, I haven't gotten an update of this, but right over the last 5 years, there has been sort of substantial movement to build offshore, particularly in the US. And so I would imagine that this is actually growing at an even faster rate over the last couple of years. All right, any questions or comments or thoughts about wind?
The capacity factor number include any losses that are part of the turbine itself, so spinning it. I'm guessing there's some losses from the drag itself. or maybe design of the blades, or can you just get maximum theoretical?
Yeah, so capacity factor is about, so it's maximum theoretical power generation should include like fundamental efficiency things within within the turbine itself. It's not talking about the percent of energy captured out of the wind. It's talking about what percentage of the maximum power generation of the turbine itself is being sort of produced over an average time period. So it should be inclusive of those things. Yeah. Okay. That is our quick flyby of wind power, unless any. All right. So next one, solar. So this, what does this look like in terms of the economics, right? So similarly speaking, it's not at the same, it's not quite as economically competitive as wind power, but it's getting there, right? So this is sort of average price. They all that the way that people talk about and depict prices and costs for renewable energies can sometimes be confusing because they can be talking about very sort of different things. So don't focus too much on the like actual numbers themselves. What I would say is like think more about sort of the trends and the direction that it's heading. Yeah, and so you can see a sort of consistent fall in the cost of producing PV installations, but it's not quite at the sort of like 10x fall that we saw with wind power. Nevertheless, installations are going up pretty rapidly, and this actually is like a incomplete year, which is why this doesn't go up higher, but it has increased in amount of capacity installed consistently every year over the last like 2 decades. Okay, some basics of how this essentially works. So sunlight comes in, right? And you have radiation hitting our atmosphere. Some of it is getting absorbed, right? So you're getting absorbed at the higher atmosphere, absorbed in clouds, and then in the ground, some of it is reflected at various levels. And so this gives like, these numbers are a fairly good representation of kind of the average over the entire globe in terms of amounts of sunlight either getting absorbed or reflected back out into space. Okay, so again, this will depend on local conditions, right? What the ground looks like, how much cloud cover that you have. But again, this is sort of averaged out over the whole globe. And then after it gets absorbed, you can have outgoing radiation of essentially all of that energy. So everything has to equal out, right? Otherwise, if it didn't, the globe would just get like hotter and hotter and hotter, right? So this is kind of what it looks like in equilibrium. Not all of this radiation that we're talking about entering the atmosphere, this 1300 watts per meter squared, can be captured by solar, right? Because you have these things happening. And so this is also averaged over the entire year. And that will fluctuate depending on sort of the angle that sunlight is hitting the atmosphere and entering into Earth, right? And so you have the highest amounts depending on the season and where you are on the planet. So it depends on atmospheric conditions, time of day, time of year, and there are even sort of solar cycles that can affect the amount of energy entering our atmosphere. So we've talked a lot about like resource potential, like how much fuel do we have, how much water do we have, how much wind do we have. Solar potential like dwarfs everything completely. So the Earth's surface, 1,000 watts per meter squared, order of magnitude, right? So if you account for weather, seasonal variations, daily variations, your annual flux is about 170 watts per meter squared, right? So this takes into account differences in seasons, night and day, all of these things. And so your total flux is about 3.9 million exajoules per year. So that is over the course of an hour, that would be the same amount of energy as all energy consumed by human activities over the course of an entire year. So strictly speaking, just the like amount of energy coming out of the sun and hitting Earth is like more than enough to power everything that we consume, like several orders of magnitude more than that, right? But we can't capture everything. Yeah, right. You let me know how that goes. Okay, solar resources in the US, Southwest, you have the most, probably not surprising to most people. And then worldwide looks something like this, right? Obviously, you're gonna have the most sort of at the equator and then the least sort of at the poles. Okay, back of the envelope for solar. So maximum insolation, so we're talking about 1 kilowatt per meter squared, sort of at the maximum. At 10% efficiency, that's 100 watts per meter squared. Your average annual insolation, 200 watts per meter squared. So at a 10% efficiency, you're getting about 175 kilowatt hours per meter squared per year. So if you remember the wind number, it was about 1 megawatt hour. So this is about 5x, a little more than 5x smaller than that. So you'd need 5 times more in terms of like area of the thing that's capturing the energy, right? So 100 meters squared to power your conventional house for the entire year. And that's actually like roughly the size of your typical rooftop. So one thing to think about there. To charge your battery car, your fuel cell car, you'd need that amount of area to get solar energy. So I often get asked this question, usually by non-technical people, but like, why not just have solar panels on your car, right? Well, because to do that like consistently and be able to power all of the electricity in your car, you would want about 20 meters squared of area, right? And so you would need like a giant roof on your car to do that, which isn't really practical. Okay, finally something different. It's not a turbine. We're not spinning anything. In fact, nothing is like physically moving, right? So this is our one sort of large power source that doesn't involve spinning a generator to produce electricity. So the way this works, you have what is known as a photovoltaic cell. You have a negative electrode and a positive electrode, and sunlight through the form of photons, right, will impact the cell. And essentially what happens is they excite the electrons, it kind of dislodges the electron, which moves it closer to the surface of the cell. And so when that happens, you have a separation of your positive and negative charges here, which creates a voltage. Okay, so that's going to induce an electrical current to occur. It's basically wanting to move these electrons in this sort of circuit, right? So that is what leads to a flow of electricity. So yeah, typical PV cells, you have silicon that is doped with boron on the positive side, and then phosphorus on the negative side. And so that's what gives you these sort of layers here that let you take advantage of these photons hitting the cells to create that voltage. From an efficiency perspective, these things are, I would say, not the most efficient, which is not, maybe that's a bad way to characterize it, but the sort of energy content of that photon, you are at the most, so the world record efficiency is about 46%. So you're capturing a little bit less than half of the energy of the photon. But for most photovoltaic cells, you're talking about an efficiency of about like 15% or so. Yeah.
So the previous slide, when we compared the area comparisons between solar and wind. So when the cross-sectional, we are taking the cross-sectional area of the turbine.
Yes.
For solar, we take the area of the turbine.
Yes.
So is there a comparison of land area for which uses more?
No. Yeah. No. Yeah. So good question. So this would be I think, more typical thing of what you would think of as a land area. But for a wind turbine, you're talking about like, it's more about the size of the blades and how much space that you have in between each of your turbines that let you sort of calculate the sort of land area. There's a homework question on this, so you'll see. Yeah.
How is the current generated here converted from DC to AC? Is that?
Yeah. Okay. Yes. So for quick refresher for everybody, so when you're spinning a turbine, the type of electricity that you're producing is AC. We're not going to get into like power systems or anything, but our electricity system operates in AC. Okay, and so for solar, this is not spinning a turbine, and in fact, the type of electricity this is producing is known as direct current. And so in order to inject the electricity generated from the solar back into the grid, if that is what you are doing, then you have to convert the electricity from DC to AC, and you also have to like step up the voltage and so on and so forth. So those processes will lead to some efficiency losses. Those efficiency losses are not included in here. But yeah, so there's a whole interesting discussion about like AC versus DC in the grid, and there's actually discussion about leaving solar in DC, especially for like distributed energy systems, right? And specifically to avoid some of these losses that you're talking about when you go from DC to AC. And that has been like a actually sort of compelling area of research. Yeah, so.
Itself, that is pretty efficient.
Yes, yeah, which also is not included in here. Yes.
Sound like
Yes. Yeah. Yeah. Yes.
Yeah, I was gonna say, someone correct me if I'm wrong, but I'm pretty sure inverting, which is the process that takes DC to AC, that's
Yep.
generally very, very.
It is, yeah.
So it's mostly think of like TTP losses.
Yeah, so yeah, inverters, you're talking on the order of like 90, 95 plus percent efficient. So you still will see some losses, and like, you know, cutting this down even more isn't ideal, but the inverter, like typically, yeah, just to give folks a sense of what those losses are like, it's not, you're not going to have like a huge amount. Yeah.
Or is that a weird one?
Sorry, you.
Does that become like more considerable when you strings of like microinverters?
Yeah, so I mean, if you do that, like you're talking about like a serial process where you're right, like 90% of 90% of 90% will eventually lead to sort of larger losses. Yeah, so you do have some issues like that.
Is there like set amount of microinverters that would like equal? Now I'm getting like too far into it, but I'm just curious.
I have no idea. Yeah, I'm certain that someone has looked at this. Yeah. Oh yeah, you go ahead.
Where does this number get the temperature? So, and when they come up with this number, what sort of conditions are they assuming that solar panels are put in place?
Yeah, so you get like lab numbers, right, which give you some indication of like efficiency under perfect conditions. But actually, when I talk about average efficiency, this is like empirical data from just like solar panels that are deployed out in the real world. So that includes all the like temperature differences that you'll experience over the year. That includes like cloud cover and yeah, dust and that sort of thing. That's all baked into this average efficiency number. Yeah. Yes.
Did I understand correctly that the loss or the efficiency between AC, DC, or vice versa is 99%? 90 to 99?
Depends on the capacity. So inverters get more efficient the more you run them.
Yeah.
So if you have more like DC to AC, that's less, right? This is transfers more than AC.
Oh, no. So sorry, just to clarify. So basically the type of the like current flowing through it, if you want to, it's not that you're getting sort of more or less current. It's like how the electricity is flowing through your circuit essentially is the difference between AC and DC. So it's not like a quantity difference. It's like changing the way that electricity travels through the circuit is your difference between AC and DC.
Okay, thank you for that.
Yeah.
And the loss is minimal.
Yeah, it's pretty small. Yeah. And the last thing that I'll say about like this efficiency number before we get too hung up on it is like that's talking about like the efficiency in terms of like capturing energy out of the photon, but like people don't really like care about that. I mean, it's not that people don't care, but like the number that we usually talk about in reference to like electricity systems isn't the like efficiency of the panel itself. It's about like how much electricity that you can get out of a system of like a certain nameplate capacity, right? So the capacity factor, which is similar, it's like 15 to 20%. So for a